Welcome, everyone. Today we're going to do something absolutely mind-bending. We are going to decode the hidden, spinning geometry of the universe itself. In this explainer, we're diving deep into a groundbreaking paradigm shift known as R-space theory. Our title today is What are Quarks? Part 1, The Mechanism of Color Confinement. So if you've ever found yourself wondering what exactly makes up the solid matter all around us, stick around. We're going to see how fundamental particles aren't just tiny hard dots, but a beautiful mathematical dance. Let's get right into it. Okay, here's our roadmap for today. We'll start with a quick refresher on the standard model basics, then move into R-space to explain fractional charges. After that, we'll break down the color confinement mechanism, look inside protons and neutrons, unpack beta decay, and finally, wrap up with the concept of particles as angular momentum. Let's kick things off with Section 1, the standard model basics. So picture this. Back in the 1930s, we basically thought the universe was just made of electrons, protons, and neutrons. Simple, right? But by the 1960s, particle accelerators had smashed that idea wide open, uncovering a chaotic particle zoo of over 100 new strongly interacting particles, which physicists called hadrons. To make sense of all this chaos, Gell-Mann and Zweig proposed the quark model in 1964. This was a massive breakthrough that beautifully organized everything into what we now call the Standard Model, defining the 17 fundamental particles of the universe. Now, under this Standard Model, protons and neutrons are built from what we call up and down quarks, and these quarks possess incredibly strange fractional charges. For instance, a proton is made of 2 up quarks and 1 down quark, giving it a total charge of +1. A neutron is 1 up and 2 downs, perfectly balancing out to a neutral charge. But here's the catch. You literally never find a quark just hanging out on its own. They're locked together by a rule called color confinement, where the strong force is handled by particles called gluons. Think of gluons like mechanical springs. If you try to pull 2 quarks apart, the tension builds and builds until the spring effectively snaps. And instead of getting an isolated quark, that snapped energy just instantly creates entirely new particles. Moving right along to Section 2, R-space and fractional charges explained. To really grasp how this works, we have to define something called a rotation vector. In R-space theory, this is the true, ultimate building block. It's basically a one-dimensional mathematical representation of angular momentum. So we need to completely stop thinking about solid bits of matter here. Instead, we are looking at pure spinning energy. And what's fascinating is that the configuration of these rotation vectors actually defines the electrical charge of the particle. To understand those bizarre fractional charges we talked about, let's use a simple analogy. In R-space, one standard rotation vector equals a -1/3 charge, and that right there is your down quark. Simple enough. But how on earth do we get a +2/3 charge for an up quark? Well, imagine a repulsive force. If you physically flip its orientation 180 degrees, it essentially becomes an attractive force. By combining and flipping these vectors in space, the geometry itself perfectly dictates those fractional charges. It's all structural. All right, Section 3, the color confinement mechanism. So, what happens when a rotation vector's energy increases? It doesn't just spin faster. Instead, its phase circle actually begins to vibrate. It's incredibly similar to the mechanics of plucking a guitar string. And this mechanical vibration of angular momentum, that is the literal genesis of what the Standard Model confusingly calls color charge. As that vibration intensifies, the simple up and down oscillation starts to map onto the rotational axis itself, completely morphing the entire structure into a distinct, three-dimensional torus-like shape. So color charge isn't some mysterious magical property. It's literally the physical, mechanical shape of vibrating angular momentum. Now, the absolutely crucial point here is what happens at very high frequencies. These vibrating vectors get so incredibly energetic that they actually link up with the main rotation vector, forming what mathematicians call a hop link. Once linked, this pair begins a complex orbital precession. And guess what that geometric dance is? That is the exact mechanical origin of an up quark. No way around it, that's what an up quark actually looks like in R-space. We can contrast this directly with the down quark. A down quark is vibrating twice as fast. Because it has this double frequency, it completes a second rotation that perfectly cancels out its own orbital precession. So from the outside, it looks simpler, kind of like a single vector. But internally, it's hiding double the vibrational energy, which brilliantly explains why the down quark is fundamentally heavier than the up quark. It all comes down to the hidden geometry. Let's move on to Section 4, inside protons and neutrons. Here, We can finally visualize color confinement not as some abstract math rule, but as a perfectly balanced three-phase alternating current, just like how red, green, and blue light mix together to form pure white light. These three vibrating angular momentum vectors, which are the three quarks, synchronize. Their vibrations perfectly cancel each other out to create an incredibly stable structure. And what about those gluons? You know, those springs holding the quarks together? Well, in our space theory, the gluon force is quite literally the mechanical springiness of the distance between these Hopf links. The overall geometry desperately wants to stay perfectly balanced and symmetrical, so the spring of the gluon is simply the system mathematically resisting being pulled out of its symmetrical shape.
Section 5. Beta decay and beyond.
Let's look at the precise mechanical steps of how a particle transforms. Step 1. If a perfectly stable proton absorbs extra rotational energy, its internal angular momentum vibrations get completely overwhelmed. Step 2. This forces the constituent quarks to literally flip their rotational states. The up quarks flip to down quarks, and a down quark is forced into an up-like precession. And step 3. This instantly transforms our stable proton into a heavier, unstable neutron. Because that new neutron state is structurally unstable, mostly due to the awkward mass balance of those flipped quarks, it really wants to return to its baseline. So it essentially just sheds that extra rotational energy in the form of a W boson. That W boson then immediately decays into an electron and an antineutrino, allowing the core geometry to snap right back into being a stable proton. That whole process, that's beta decay, visualized entirely through structural geometry. It's also worth noting that inside an atomic nucleus, protons and neutrons are constantly exchanging this rotational energy in a never-ending cycle. It's like an incredibly fast game of hot potato, and this rapid, continuous swapping is what actually maintains nuclear stability. In essence, a nucleus is just a cluster of protons sharing electron-like rotational components to remain bound together. And finally, Section 6, particles as angular momentum. When we bring all of these concepts together, our space theory delivers a truly profound unification. It tells us that quarks, electrons, and photons are not fundamentally different things at all. They are all just vortices of angular momentum. In fact, an electron is quite literally a state where the angular momentum of a photon has been folded in on itself and trapped by the exact same color confinement mechanisms we just discussed for quarks. Everything is beautifully geometrically unified. I want to leave you with this final provocative thought. If everything around you, from the light hitting your eyes right now to the solid device you're watching this on, is ultimately just different states of trapped, spinning geometry interacting with each other, how does that change your fundamental understanding of reality itself? Thank you so much for joining me on this incredible deep dive in today's explainer. Stay curious, keep visualizing, and I'll catch you in the next one.